Welcome everyone. This is Shakir Samanthapudi. Today I will be presenting on feature projection techniques, PCA and LDA. This topic is crucial for understanding how we can reduce the complexity of high dimensional data while preserving its most important features. Let's dive into why these techniques are essential and how they work. Like as an overview, the presentation will cover three main topics: PCA, LDA, and a detailed comparison between the two techniques. And also, by the end of this presentation, you will have a clear understanding of when and why to use these methods in your data analysis workflows. And before entirely diving into this presentation, uh, we will discuss why do we need feature projection techniques. In real world scenarios, datasets often contain numerous features. This lead to high dimension spaces. This can confuse the machine learning models and result in slower time training times, and also overfitting and poor generalization. Uh, and here, the feature projection techniques like PCA and LDA helps to address these challenges by reducing the dimensionality while keeping the essential information. So we will discuss the challenges with high dimensions. The high dimensional data is problematic because it increases the computational complexity, and it also introduces the noise or redundancy. And by this, the models may struggle to identify the meaningful patterns and may lead to overfitting. So here, feature projection techniques simplify these by transforming the data into lower dimension without losing the critical information. We can also get benefited by the feature projection, like it reduces the dimensionality, removes the noise and redundant features, and also improves the model performance and training speed, and makes the data to easier to visualize and interpret. These benefits are especially useful in applications like image processing and medical diagnostics. And we will see what is PCA. PCA is an unsupervised technique that transforms the higher dimensional data into lower dimensional data while maximizing the variance. And it identifies the patterns in the data by finding directions or axes, which are called as principal components, which are along with the data, and the data varies the most. And this makes PCA ideal for simplifying complex data sets. And why why it works on transforming the data from higher dimensional to lower dimensional. PCA will be finding the orthogonal directions that represent the new axis in the feature space. These principal components capture the maximum variance in the data while eliminating the noise and redundancy, and also projects the data onto these components, so we preserve essential patterns with fewer dimensions. So the key idea here is variance will be maximized without losing the information. And we will be seeing the steps to perform CPCA, like the mathematical interpretation. Like initially, the first step is to standardize the data so that all features contribute equally regardless of their scale. So by this formula, X is the initial feature matrix, and mu is the mean of features, and sigma is the standard deviation. And let us see how to compute the second step. So we calculate the covariance matrix to measure how features vary together. By this formula below, we can see how features vary together. And next, eigen values and vectors. How these are useful in this? So we will see eigen values represent the variance explained by each principal component, while eigenvectors define the directions. So, using this formula, we can find the eigenvectors W, where C is the covariance matrix calculated here. So, the next step, we sort the eigenvalues in descending order and select the components with the highest values. And finally, we will project the data onto new axis using principal components, where T is the transformer data and X is the initial matrix and W is the eigenvector matrix. So, if you see this example, this is the matrix X. We have two features with values, and the first step will be subtracting the mean divided by standard deviation for each feature. Then we will be getting this covariance matrix, and we'll be calculating the eigenvalues and the eigenvectors for these eigenvalues. So we'll be projecting data that will be the uh, transformer data using principal components. And let us dive into LDA then. LDA. LDA is a supervised technique which is designed for classification tasks. Unlike PCA, LDA focuses on maximizing the class separability by finding linear combinations of features that bestly distinguish between the classes. And these are used in pattern recognition, face recognition, medical diagnosis, in advanced applications. And let us see why it works on dimensionality reduction or feature protection. LDA works by maximizing the between class variance while minimizing the within class variance. This ensures that classes are well separated in lower dimensions, so making it ideal for classification problem with labeled data. So the key idea here is it will be focusing on maximizing the between class and minimizing the within class variance, so which can enhance the classification performance. So next, the mathematical interpretation follows. Initial step will be calculating the class mean vectors. Like we start calculating the mean vectors for each class using this formula, where mi represents the class mean of each feature. And second step, we will be carrying the calculation of within class scatter matrix. Within class scatter matrix measures the spread within each class. So using this formula, we will be calculating within class scatter matrix SW. And the third step will be calculating between class scatter matrix. So this tells us the measure the measure of separation between each distinct or unique class, where m here is the overall mean and mi is the mean of that particular class, and sp is the between class scatter matrix. And the fourth step, this is the optimized step, where we will be maximizing the between class separability and minimizing the within class separability. So using this formula, w is eigenvectors, Wt is the eigenvectors, and Sp is between class scatter matrix, Sw is within class scatter matrix. And let us see, using this example, we are having two features here. 422, 242 are the feature values of class 1, and for class 2, these are the feature values 10, 12, 14 of feature 1, 10, 12, 14 of feature 2. So we'll be computing class mean vectors. Class vectors will tell the means of each feature, and we'll be calculating within class scatter matrix. And then we'll be calculating between class scatter matrix SB. So by calculating this, SW inverse product with S between matrix, we'll be getting W. So this is the optimized step when we have solved the eigenvectors. So this will be multiplied into the initial feature matrix. Then we'll be getting the linear discriminant analysis LDA component. So it can be used for predicting the classifications. So the closing slide, which will be telling a detailed comparison between PCA and LDA. So PCA is a unsupervised learning technique, while LDA is supervised learning technique. Because LDA will be taking class labels for computing, and the objective of PCA is to find the principal components that maximize the variance without losing the information retention. And while LDA's all objective is to find the linear discriminants that maximize the separation between multiple classes and minimize the separation between within the classes. Like we can see that PCA will not use class label, so it is unsupervised, and LDA uses the class label, so it is supervised. And the computation in the PCA follows as eigen decomposition of the covariance matrix, while here the computation follows as eigen decomposition of between class matrix and within class matrices. So the final projection goal of PCA is to project onto the directions with maximum variance to reduce the dimensionality from higher to the lower or some desired dimensionality. And in LDA, the goal is to project onto the directions which will maximize the class separability between the class and minimize the class separability within the class to achieve a better classification. So in summary, both PCA and LDA are powerful tools for dimensionality reduction, but serve different purposes. So, understanding their strengths and limitations allow us to choose the right technique for specific tasks. So, thanks for your attention. Thank you for giving this opportunity. Have a good day.